Chapter 9, Photoelectric Effect. Let's talk about light. Now, we have seen that when a metal surface is sufficiently heated, it emits electrons in a process called thermionic emission. It turns out, when an electromagnetic radiation of sufficient frequency is radiated on a metal surface, electrons are emitted. These electrons are called photoelectrons, and the process is called photoelectric effect. Photoelectric effect was accidentally discovered in 1887 by Heinrich Hertz while conducting an experiment on the production of electromagnetic radiations, but he didn't pay much attention to this new phenomenon. Instead, this phenomenon would be thoroughly investigated by two other scientists, Wilhelm Hallwachs and Philip Leonard, between 1886 and 1902. Leonard conducted an experiment in which he placed two electrodes, a cathode acting as an emitter and an anode acting as a collector plate inside the vacuated glass tube. He connected the plates to the respective terminals of a battery by a wire through a sensitive ammeter to measure any current in the circuit. He then allowed UV radiation to fall on the cathode or the emitter plate. As soon as the radiation fell on the cathode, a current flowed in the circuit as indicated by the ammeter. He also observed that as soon as the UV radiation was stopped, the current also stopped flowing in the circuit. This experiment showed that the cathode emitted electrons when struck by the UV radiation. These electrons were attracted by the positive anode and flowed towards it, ultimately setting up an electric current in the external circuit. Wilhelm conducted a further but simpler experiment to advance this new phenomenon. He mounted a clean, circular, negatively charged zinc plate on an insulating stand and connected it by a wire to a gold leaf electroscope. He observed that when UV radiation struck the zinc plate, it lost the charge. He repeated the experiment by replacing the negatively charged plate with an uncharged one. When UV radiation hit the plate, it became positively charged. Moreover, using a positively charged zinc plate in the experimental setup further enhanced the positive charge of the already positively charged zinc plate. From these observations, he concluded that negatively charged particles were emitted from the zinc plate on being radiated with UV light. During the experiments, Leonard and Hallwachs also observed that no electrons were emitted by the surface when the frequency of the light was less than a certain minimum value. This minimum frequency of incident light below which no photoelectrons are liberated from the metal surface is known as the threshold frequency, F0. The wavelength corresponding to the threshold frequency is called the threshold wavelength, lambda naught. This frequency depends on the type of metal surface. Metals such as zinc, cadmium and magnesium respond only to UV light because it has short wavelength, while others such as lithium, sodium, potassium and cesium are sensitive even to visible light, which has a longer wavelength. So, how comes light is able to dislodge electrons from metal surfaces? Let's talk about light energy and the quantum theory. So, up until now, we have known light to behave as an electromagnetic wave. It is therefore also called electromagnetic radiation. Light waves have both wavelength and frequency, that is the number of cycles passing through a point per unit time. They are inversely proportional, since the shorter the wave, the more of them that can go by per second, resulting in a higher frequency. These variables are related by the formula c is equal to f lambda, where c is the speed of light, about 300 million meters per second. The electromagnetic spectrum shows radiations of different wavelengths from gamma rays to radio waves, including this tiny part in the middle, which is visible light. The understanding of light as a wave was useful for a long time, but it could not explain the photoelectric effect. And the confusion was that the ability of light to emit an electron depends only on its frequency and not its intensity. So if the beam was below the threshold frequency, even the intense beam with a lot of light could not eject an electron. Whereas above the threshold frequency, even the faintest beam possible could do it. This sent scientists back to the drawing board until a famous scientist, Albert Einstein, solved the puzzle by advancing a concept developed by another scientist, Max Planck, 5 years earlier. According to Planck, energy is not continuous, but rather quantized. That is, all energies are multiples of the smallest fundamental unit of energy, called the Planck energy. This simply means that you cannot infinitely subdivide energy. You will eventually get to the smallest amount that cannot be divided further. With this understanding, Einstein explained that light must also be made up of quanta, which he called photons. These are particles of light. This explained the photoelectric effect because an electron is ejected when struck by a singular photon with sufficient energy. It only takes one photon, so even the faintest beam above the threshold frequency will be able to do it. But if none of them is above the threshold frequency, no matter how many photons strike the sample, an electron will not be ejected. It was found that the energy E of a photon can be given by the formula E is equal to hf, where h is the Planck's constant, equal to 6.63 times 10 to power negative 34 joules second, and f is the frequency of the photon. From the wave equation, C is equal to f lambda, it means that f is equal to c over lambda. Substituting f in the expression for energy of a photon, E is equal to hc over lambda. Considering that Planck's constant and the speed of light are constant, it means that a light wave with a shorter wavelength has more energy. So now we know that light obeys the wave-particle duality, meaning that it is both a particle and a wave at the same time. Let's talk about Einstein's equation of photoelectric effect. Now, when photons are incident on a metal surface, the metal electrons absorb energy from the photon. The minimum energy required for the electron to just dislodge from the metal surface is called the work function, W0. This energy is generated when the frequency of the light wave is equal to the threshold frequency, F0. So work function is equal to h F0, which can also be expressed as work function is equal to hc over lambda naught. This energy differs from metal to metal. Work function is given in a unit called electron volt or joules. 1 electron volt is equal to 1.6 times 10 to power negative 19 joules. If the energy absorbed by the electron is greater than the work function of the metal, the electron is dislodged with maximum kinetic energy, Ke max equal to E minus work function, where E is the energy of the incident photon. This is called the Einstein's equation of photoelectric effect. This equation can be expressed in different formats, but it doesn't change the overall meaning. For example, we know that kinetic energy is equal to a half mv squared. So maximum kinetic energy is equal to a half me Vmax squared, where me is the mass of an electron and Vmax is the maximum speed of the electron. Also, E is equal to hf. Substituting all this in the Einstein's equation, a half me Vmax squared is equal to hf minus work function. This is still Einstein's equation. Further, E is equal to hc over lambda, and work function is equal to hc over lambda naught. So, a half me Vmax squared is equal to hc over lambda minus hc over lambda naught. Factorizing the right-hand side of the equation, a half me Vmax squared is equal to hc into 1 over lambda minus 1 over lambda naught. Let's take two examples. First one, the energy of a photon of violet light is 4.97 times 10 to power negative 19 joules. Calculate its frequency and wavelength. So, we know that energy is equal to hf. So 4.97 times 10 to power negative 19 is equal to 6.63 times 10 to power negative 34 times frequency. To get frequency, we divide both sides by 6.63 times 10 to power negative 34. That gives us frequency is equal to 7.50 times 10 to power 14 Hertz. Then we calculate the wavelength. C is equal to f lambda. 3.0 times 10 to power 8 is equal to 7.50 times 10 to power 14 times lambda. To get lambda, we divide both sides by 7.50 times 10 to power 14. That gives us a wavelength equal to 4.0 times 10 to power negative 7 meters. Second example. The work function of a certain metal is 3.56 times 10 to power negative 19 joules. When the metal surface is irradiated with a certain source, photoelectrons are dislodged at a speed of 7.9 times 10 to power 5 meters per second. Calculate A. The threshold frequency of the light that will cause emission from the metal surface. B. The maximum kinetic energy of the photoelectrons. C. The energy of the photon. And D. The wavelength of the source of radiation. So, work function is equal to Planck's constant h times the threshold frequency f naught, meaning that f naught is equal to work function over the Planck's constant. That is 3.56 times 10 to power negative 19 over 6.63 times 10 to power negative 34. That gives us 5.37 times 10 to power 14 Hertz. Maximum kinetic energy is equal to a half me Vmax squared. That is a half times 9.11 times 10 to power negative 31 times 7.9 times 10 to power 5 squared. That gives us 2.84 times 10 to power negative 19 joules. Energy of the photon. Maximum kinetic energy is equal to the energy of the photon minus the work function, which means that the energy is equal to maximum kinetic energy plus the work function. That is 2.84 times 10 to power negative 19 plus 3.56 times 10 to power negative 19. That gives us 6.40 times 10 to power negative 19 joules. finally, the wavelength. We know that energy is equal to HF, or energy is equal to hc over lambda. This means that lambda is equal to hc over E. So 6.63 times 10 to power negative 34 times 3.0 times 10 to power 8 divided by 6.40 times 10 to power negative 19. That gives us 3.11 times 10 to power negative 7 meters. Now we move to factors affecting photoelectric effect. Now, the ability of a radiation to emit photoelectrons from a metal surface is determined by the intensity of the radiation, the applied potential difference between the two plates, frequency of the radiation, which of course determines the energy of the radiation, and the type of material. Intensity of radiation is the amount of energy incident on a unit area in a unit time. That is, intensity is equal to energy over area times time. This is also equal to work over area times time. But work over time is equal to power, and so intensity is equal to power over area. As you increase the intensity of radiation incident on the metal surface, it is observed that the photoelectric current increases proportionately. This is because as the intensity of the radiation increases, the number of photons incident per second on the metal plate increases. This results in the number of emitted electrons increasing and hence increases the photoelectric current. Second factor is the applied potential difference. As you gradually increase the accelerating potential across the emitter and the collector plates, you will notice that the current in the ammeter increases. This happens due to an increase in the number of electrons that reach the collector plate per second. As the accelerating potential across the emitter and collector plates increase further, you will notice that current in the ammeter reaches its maximum and remains constant. This maximum value of current is called saturation current. Saturation current is a consequence of all the photoelectrons emitted by the plate C reaching the collector plate E. Now suppose we reverse the polarity of the battery. This potential builds a positive charge on the emitter plate that attracts the emitted electrons, and a negative charge on the collector plate that repels the emitted electrons. This potential is called retarding potential. As the retarding potential increases, you will observe a sharp decrease in the photoelectric current. This is because of the decreased number of electrons that reach the collector plate. As the retarding potential difference increases further, at a particular voltage, negative V0 applied to the anode, the photoelectric current becomes zero. The maximum negative potential V0 applied to the anode, for which the photoelectric current becomes zero, is called the stopping potential or cutoff potential. The photoelectric current becomes zero when the retarding potential becomes strong enough to repel all the photoelectrons with the maximum kinetic energy. The maximum kinetic energy of the photoelectron is equal to eV0. This is equal to the work done by the stopping potential, meaning that eV0 is equal to a half mv squared. Substituting in Einstein's equation, E is equal to eV0 plus the work function, or HF is equal to eV0 plus HF0. So eV0 is equal to HF minus HF0. third factor is frequency of the radiation. When radiation of increasing frequency of same intensity is incident on the emitter, the number of photons incident per second is the same, and hence the number of electrons emitted per second will be the same. Therefore, the saturation current is observed to be the same, although the stopping potentials are observed to be increasing. As the frequency of radiation increases, V0 increases as well. This implies that the maximum kinetic energy of the ejected electrons also increases according to the relation Ke max is equal to EV0. But the maximum kinetic energy is independent of the intensity of radiation. It is observed that for copper, UV radiation can produce the photoelectric effect, but radiation of lower frequencies like green or red does not cause photoelectric emission. This shows that for every metal surface, there exists a minimum frequency of radiation which we call the threshold frequency F0, lower than which photoelectric emission is not possible regardless of how high the intensity is. Threshold frequency is different for different materials of the emitter. This means that although the stopping potentials vary in a linear fashion with the frequency of the incident radiation, for a certain minimum frequency, the stopping potential is observed to be zero. This was observed to be true with different materials as emitters. For the same intensity and frequency of light capable of causing photoelectric effect on different emitters, the photoelectric current remains the same, which proves that photoelectric current is independent of the material of the emitter. Finally, applications of photoelectric effect. First, photoelectric cell. A photoelectric cell is an electron tube in which the electrons initiating an electric current originate from photoelectric emission. It consists of a cathode coated with a photosensitive material and an anode. Light falling on the cathode causes dislodging of electrons, which are then attracted to the positively charged anode, resulting in a flow of current proportional to the intensity of the incident radiation. Phototubes are either evacuated or filled with an inert gas at low pressure to achieve greater sensitivity. It is applied in photosensor motion detectors used in burglar alarms, traffic light controls, and automatic door openers. Others are used in sound recording, televisions, and scintillation counters. In a home security system, the light produced by a bulb at one end of the circuit falls on a phototube some distance away, and electrons are emitted by the cathode. When a person walks between the light source and the phototube, the beam is blocked briefly. The tube registers a drop in light levels and sends a signal to the control box, which is connected to a siren or a telephone auto dialer. A solar panel is used to produce electricity, and its working principle is based on the photoelectric effect.